I love this event that we're bringing together academics and industry types. And I work for Microsoft in fact, I'm both. I work for Microsoft in Cambridge in the UK, and I'm also part-time at the University of Edinburgh. So this talk is about a hot topic in, I guess, programming languages for machine learning at the moment, this idea of probabilistic programming. And that's the idea that you can write a probabilistic model of data as a bit of code, and if you were to run it, you'd get sort of synthetic data. But then if you compile it in a certain way, you can turn it into inference code that will learn parameters and make predictions from actual data sets. And we've looked at this problem, and we said, well, look, where should we be doing this? We should be doing this where the data is. We should take the code to the data. And an awful lot of the world's data lives in spreadsheets. So this project, which is codenamed Tabular, is all about taking this sort of the research that's been done on probabilistic programming languages and embedding it within a spreadsheet environment, so that people who are not necessarily developers are able to do their machine learning using probabilistic programming within the spreadsheet. But to begin with, I want to give you an idea of probabilistic programming. And what I'm going to do is give you a little sort of probability puzzle, and I'll tell you it in words, and then I'll show you how we can write it in code. So, imagine you're an English country house, and there's been a murder. Let's say Professor Plum has been found dead. You know who has killed him, and Alice and Bob are in the frame. And a priori, if I'm the detective coming to the house, I think it's most likely that Bob done it. So it's a 70% chance Bob done it, 30% Alice done it. And then there's two possible weapons may have been used. We don't know which at this point. But we do know that Alice would really prefer to use the pipe, 97%, and Bob would much rather use the gun. So that's our sort of probability situation before we've actually visited the scene. So how could we write that as code? Here's a little bit of code that does it. So I first of all have a Boolean variable that is true for Alice done it, false for Bob done it. And so we flip a coin. So I assume I've got some sort of random primitive that takes a probability and it tosses a coin. So this is going to come up 30% of the time true to indicate Alice done it, and 70% false to indicate that Bob has done it. And then the second variable is whether the gun or the pipe has been used. And that is conditional on the first variable. So if Alice has done it, she's only got a 3% chance of using the gun, whereas if Bob's done it, he's got an 80% chance. So this is our model of the situation. And the way that the really simple way to understand how we're defining a probability distribution by a bit of code is if you think about just running the program many times and then counting up the different possibilities. So this is called sampling. And so if you were to run this program many times, this is the distribution of the four possible values you'd get. So it's most likely that it would be Bob using the gun. So it would come up here, and then less likely Bob using a pipe, and I think it's something like 30% chance it's going to be Alice using the pipe, and very unlikely that it's Alice using the gun. So that's a sort of prior situation. So this is, and then we actually visit the scene, and it turns out that a pipe was found at the scene. So this now lets us update our model of the situation in light of this data. And the way we would represent that is imagining we have a sort of assertion within our programming language called an observation. It's an assertion that constrains the variables. In this case, we constrain that with gun is false because it was the pipe that's been used. And you could, again, what does this mean operationally? Well, we're interpreting a probabilistic programming by running it many times. And what we're going to do is mark some of the runs as invalid. They're incompatible with the data. So we're going to chop out those runs. And in this case, we're going to chop out the situation where with gun is false. So we're going to chop out all the cases where where it was the gun that was used. And so you get this sort of thing. So basically, I basically removed these possibilities and then renormalized. And now the situation is flipped around. So to begin with, we thought it was most likely that Bob has done it, but in the world in the light of the data, it's much more likely that Alice has done it. And in probability notation, we'd say at the top what this graph is showing is just the chart of these events, the probabilities of C and W, and down here it's the probabilities of C and W happening given that the width variable, the actual weapon, was the pipe. So that in a nutshell is probabilistic reasoning. Sometimes people call this Bayesian reasoning about a situation where we represent, we have some sort of, sometimes it's called a generative model, or we have a probabilistic program that represents our view of how the data is generated, and then we place constraints on the actual generated data in light of the data. So you can do probabilistic programming in lots of different languages, and I mean, you can be functional, you can be imperative, and there's really three things you add to your language to represent probabilities. One is some sort of randomness, so you can toss coins, you can roll dice, you can also draw from, say, Gaussian distributions to get numbers. You have constraints like my observe equal operator, and generally what you're observing is that some synthetic value of the data equals the observed data. And then finally, you're trying to infer some variables. In this case, it was whodunit. So you have to some way of saying which variables it is you want to infer. And in any of these systems, the kind of the rallying call for why you're doing this is that it's much easier to represent, to write code that sort of simulates a situation and then have the compiler generate inference code that will learn your parameters and make predictions than it would be to do all that from scratch. So typically, the programs you write are very short, maybe 10, 20 lines is very, very typical, but the equivalent inference code would be thousands of lines, and the compiler will generate that automatically for you. Now, there's lots of systems out there, most of which are sort of in the research community, but I call out this one bugs. So BUG stands for Bayesian inference using Gibbs sampling, and this is the granddaddy of the field. And that goes back to the early 90s, and this is actually quite widely used in practice. And then there's a great many other systems, like Church is like probabilistic programming in Lisp. What else? Hansai is sort of probabilistic programming in OCaml. The system that we're building on is called infer.net, and it's probabilistic programming in C#. And we did a version that uses F#. But what I'm going to talk about today is using Excel and a range of other such languages. And if you want to understand the semantics, there's a bunch of nice work using the probability monad. So if people are interested in monads and what have you, it's a dangerous topic to bring up. There's some good papers to go and read about how that is done, but I'm not going to go into the details of that at all today. And this is a slogan from Kathleen Fisher, really that about the general aims of the field. That we want to sort of make development of machine learning systems as easy as easy as just writing short bits of code. It's as if we've been in the world of assembly language and machine learning, and we want to kind of raise the level of abstraction. So finally, this talk, and I'd like to get onto a demo very quickly to show you doing machine learning inside Excel, but I want to say a bit about our intentions. There's a range of populations of users we'd like to reach out to. So there's a small kind of group down here, the machine learning PhD, someone who actually is a specialist in machine learning, who's capable of writing the inference code from scratch. Then there's a larger population of users, the ML developer, someone who's maybe a C# or a Java programmer who would like to, who's trying to build machine learning systems. We'd like to enable them. Then there's the data scientist, someone who's maybe a statistician by training who uses R, and maybe he's not so much of a programmer but knows a lot about stats. And then there's the data enthusiast. And so this is the sort of the person, the business person, or the scientist, maybe a doctor who is curious why it is that some patients return quickly to the hospital and not others, or the car salesperson wants to know why some cars do well at auctions and others don't. Someone who cares seriously about their data and has some sort of business, professional reason in understanding it better. There's lots of those people, and we'd like to reach out to them. I'm afraid at the moment our system is probably best used by machine learning PhDs, so we've got a bit of a journey to make it more usable. But the first step is getting into Excel, and then we're going to try and make it more automatic. So we've got three guiding principles. You can't do machine learning without data, and therefore you're going to have some sort of data schema, typically a relational schema, a bunch of tables with foreign key relationships between them. And the basic idea of tabular is it's a domain-specific language that starts from that schema and lets you mark it up with probabilistic annotations that explain how the data is generated. And then we can do inference. We do inference. We choose which variables to query by just leaving blanks. So I'll show you that in a moment. So we just leave blanks in a column in Excel, and then the model will try and fill them in. And finally, I won't say so much about this, but this is our aspiration. We think at the moment our system is usable by this sort of the darker kind of hues down here. We'd like to go up to the lighter ones, and to do that, we want to auto-suggest models that will be useful in different circumstances. And we've made some progress in that, but we're not kind of done. All right, so Excel. Okay, so here's a tiny data set, and this is a problem of ranking, okay? So I've got a table of players, Alice, Bob, and Cynthia, and I've got some matches between them. So Alice plays Bob, and this is saying that this is a Boolean saying whether player 1 has won or not, okay? So in this case, it's saying that Alice lost to Bob, and then this is saying that Bob lost to Cynthia, and I've left a blank. I'd like to fill this in. Perhaps Alice and Cynthia are going to play tomorrow, and I'd like to infer how likely it is that Alice is going to, beat Cynthia. Perhaps I want to decide whether to take a bet or not. So that's the data I have, and I will start up Tabular. I should say that Tabular is a download from the Microsoft Research website, and you're free to download it. I'll give you the URL in a moment. So Tabular's up there. We start it on the side. And one thing I should say is that we are using a feature of Excel that's fairly recently been introduced, that it builds in a relational data model. So we're not extending Excel's formula language to do probabilistic modeling. We're sort of extending the relational model that's built in. So this UI here is just this data model. So you see it's got a table here of the players and a table of the matches. But I'll just put that to one side. So the first thing I can do is ask Tabular to fill in a default model. Okay, so Tabular knew, I had preloaded actually, I told it that there were two tables, the table of players and the table of matches. And if I make this a bit bigger, you've got a chance to see. Okay, so this is a simple tabular program. So tabular programs are sort of Fortran-like. They sit in 4 columns. This column here, column A, has got the name of the columns in your database. So the players database at the moment has got no columns apart from the primary key, the name of the player. And the matches table has got three columns. It's got player 1, player 2, and win 1, which is a Boolean. And we filled in a default model, which won't do a very good job of inference, so I'm not going to use it. So what I will do is, well, I can show you it. Let me run it. So what it's done is over here, it's done inference, and it's put the results back into the spreadsheet. Okay? So, and in particular, it thinks there's a quarter chance that Alice will beat Cynthia. And it's done that just on the basis that player 1 has tended to lose to player 2. So it's got no kind of knowledge about the actual skills of the players. Okay, so let me just delete the results. Let's go there. And then we come back here. And so what I'm going to do is a model called TrueSkill. And the idea is that every player has got a latent variable, a hidden variable, that is their skill. It's a number. And let's say that it's the number with mean 25 and standard deviation 10. So roughly it's between nothing and 50. And then the model is that when 2 players meet, the one who's got the higher skill is going to win, probably. Okay? So let me write that. So I add a column called skill. I say it's real. I say it's a latent variable. And I'm going to say it's a Gaussian. And it's going to have mean 25 and standard deviation 10, you write the square of that, the variance. Okay, and then down here, I'm going to predict who's going to win or not by saying player1.skill if that's bigger than player2.skill. Cool. So let me just make that a bit smaller. So let's run inference. So it thinks a bit, and during inference what it's done is it's compiled down to the infer.net system, which is down to a sort of probabilistic program in C#, run that, got the results, and then put them back in the spreadsheet. And let's go look more closely. This is going to be a bit small. Let me first of all look at the skills. Make this a wee bit bigger. So these started out as being everyone was 25, but Alice lost to Bob, and Bob lost to Cynthia. So what it's learnt is that Bob is in the middle. Whoops, how did that happen? Interesting. Did it again. What was that? Right. Okay, live demo. That's never happened before. Okay, let me just point. So, whoops. So Bob is stuck in the middle, still at 25, but notice that the variance has gone down, right? So initially I was very uncertain about Bob's, or everybody's skill. It was like, it was like spread out between nothing and 50. But you see that this has dropped down to 45 from 100. So this is, and when people say Bayesian or probabilistic inference, what they mean is that the answers you get at the end are not yes, no. It's not like a, or a specific number. It's more like a distribution, right? And in this case, it's a Gaussian distribution, a bell curve. And so your answer is it's still mean 25, but it's become more precise. The variance has dropped. And you'll see that Alice is down at 16 and Cynthia is up at 33. Now, this is a very crude model because, well, hold on, okay. And then the other thing is, we've made a prediction. So we think there's just a 5% chance that Alice is going to beat Cynthia. And that's because Alice's skill is much lower than Cynthia's skill. And this is really rather crude because I've said that there is an exact skill that everybody has and that exactly determines who's going to win in the particular match. But we all know that almost every kind of game has got some element of chance, and moreover, people's skill, it's a bit of a fiction. Maybe you had to skip lunch because things are running late, and so your skill is not quite what it was. So we need to take that into account. So the way we can do that is by putting a bit of noise into the model. So if I go in here, what I can do is, instead of just using the exact skill, what I can do is, I can put a Gaussian. So basically add a bit of noise. So I'll add the same amount of noise, a Gaussian with mean as the skill, and the standard deviation being 10 again. Okay, and so now I've got a type checking error. Wow.
Put a comma in the second hundred.
Thank you. I've lost it now. Ah, yeah. Thanks. Okay, so now if I rerun inference, you see that, so now we're a bit less certain about our observations because we've added a bit of noise. So what you see is that the skills haven't moved so much, and in particular the variance hasn't gone down so much because we've added some noise. And the other thing you see is that the prediction is much less certain. It's no longer a 5% chance. It's gone up to a 30% chance. Okay, so that was a quick demo. Let me see. I've got a pre-prepared spreadsheet with a more complicated thing to show you that we don't just do very simple things like that. So this was one of our early users did a model of American college football. So the same kind of idea that college football teams were given skills, and this was used to predict how they did in their leagues. And the model was, I don't think this is going to be very as usable, as visible as I like, but the model is basically a little more sophisticated, but it has the same kind of structure and is written in 22 lines of tabular. So one of the differences, I take my chance again with this. Well, whatever. One of the differences is, and I've got a table of leagues. So and every team belongs to a league, and so we can have a skill associated with a league. And then, and every team skill is a sort of noisy copy of the league's skill. So that means that, and the reason you do that is you expect that different leagues are going to have, each league is going to have teams that are sort of comparable with one another. So once you start to learn about the behavior of other teams in the same league, you'd like to learn something about, another team in that league. And the way we do that is to have this shared league level skill. So that's one difference with the simpler model. And the other one is we also take into account whether a team is playing at home or not. And we have an additive home skill advantage that we add to the skill of the player that was, the team that was playing at home. So this is actually an external user who was an ML PhD, but he was able to use the system, and he did some nice visualizations. And this is really, and this sheet kind of shows you why I think it's so nice to work within Excel, because you can have the data there, you can have the model there, and then you can visualize the results. And it's all just something you can save and email to someone. So these are the results he got. Oh, heavens. I should stop doing that. At the top you see, that's the skills of the teams sorted by their mean. But then more interestingly, just to compare to human-derived judgments, there's, I think, an Associated Press set of experts that rank teams as well. And this plot here is plotting the skill against the rank of the, from the experts. And you can see that it's, broadly speaking, a downward sloping line, which is what you'd expect, correlation between the two. So basically, the model is recovering largely what the human experts considered was a reasonable ranking. Okay, so let me return to the talk. Okay, so I'm self-chairing. It's 2:30, and I started at 10 past, so got until about 22:22, 10:02. Are there any questions at this point? You've been remarkably silent. Post-lunch, I suppose. Okay. Right, so let me skip on. So we went through, these are my backup slides in case things crashed. This is to give credit that the underlying system we use is called Infer.net. It's been developed for about 10 years in MSR Cambridge, developed by John Wynn and Tom Minka. And it's a language that lets you use C# to describe probabilistic programs, and then they build various inference algorithms, and what we're doing is building on top of that. Okay, and I've shown you this sheet. So generally, I've given you the demo, and what I was showing is this recipe for how we use tabular. You start with a schema. You add latent columns that describe qualities of the data, such as the skill of players, and you write models for those latent columns and output columns, such as the thing, and outputs of things you're trying to predict, such as who's going to win. And then by running tabular, we learn these the columns and the parameters and predict missing values. And the tabular language itself focused really just on this part of the cycle of developing a machine learning model. But I mean, the whole experience is much more than that. And we decided to embed in Excel because we figure Excel is a great place to do visualization and data wrangling and so forth that are all sort of very important to building machine learning systems. Okay. So let me go more slowly through the different components of the language. This linear regression here is going to illustrate the idea of parameters, which I haven't shown you so far. So what's linear regression? Well, you have a bunch of points, and you want to find the best fitting straight line that goes through them. And if we phrase this as a probabilistic question, your model of the data is this, that you, for every pair xy, you expect that y equals x times a plus b plus some noise. So b is like a global shared intercept, and a is like the slope of the line, and e is some noise. There's always the discrepancy between the line and the actual point. And you want to, and you can phrase this as trying to minimize the total square errors. Would be if you're not being probabilistic, that's how you'd say it's an optimization problem. You're trying to find the A and the B that minimize the square of all the errors. Instead, we formulate it probabilistically, and I'll show you that in tabular. So for this data set, the only actual observed data are the blue and the orange lines. That we have a bunch of x's that are reals, and we have y's that are also reals. And these gray columns are all the rest of the model that you'd have to add. And the crux of it is that down here we say that in every row that there's a z, which is the actual point on the line, which is ax plus b, and then y itself, the observed item, is a sort of noisy copy of z. So just as I made noisy copies of skills in the previous example, here I'm making a noisy copy of the point on the line. And how do you find a and b? Well, they're declared as parameters, and the difference between a parameter and a latent variable is that the latent variable is added in every row of the table, whereas the parameter is like a global. It's like a static. It's sort of the difference between static and instance variables, so to speak. And here we declare A and B. We don't know what they are, so we say they're noisy copies of some what are called hyperparameters, which are both, in this case, just going to be 0. So we've got some sort of model about our uncertainty about what A and B are that we stipulate here, and then we use them to define the rest of the model. So that's linear regression. And you can visualize this as something called a factor graph. And this is essentially what we send to infer.net. And in this, so this is like very much a probabilistic model. So the circles are random variables, and the square boxes are what are called factors, and they're basically computations that will compute one of the random variables from one of the others. So you can see at the top, we're computing B and A by doing Gaussian draws. And then down here, inside this thing called a plate, we take an X and then as an input, and then do the computation to produce a Z, add some noise, and you get the output. And this box here is known as a plate, and basically it's a for loop, or it's a map over all the items in the table. So this is like an equivalent, well, a way of rendering what the tabular model is. Okay, so how might you use this? Well, here's an example of using it to do price or determine price elasticity, which is the property it's the property of whether or not when you put the price up of some item that you're trying to sell, the sales volume goes down. So here I've got a bunch of data, and this is from some classic sort of management science study or marketing study, where they had data on sales of cheeses in various American cities and in different retailers. And they've got a whole lot of observations of when there was a particular price, like $2.57, the volume was 21,000 at a particular retailer. So you've got a table of price, volume, and retailers, and then you've got a table of retailers. And if you visualize the data inside Excel, you get this sort of picture where there's a gentle slope going down, but you haven't learned anything about what happens at different retailers and what the relationship is. And then the point of a sort of probabilistic model of this, and in particular one that is hierarchical in the sense that we group the observations by the retailer, is that you can see the differences between retailers. So we can write this in tabular as follows, where this is the tabular program for the retailers table. This is the tabular program for the sales table. And the key thing is that I've got a slope associated with every retailer, and that the mean of the slope itself is a shared parameter. Okay? So we're sharing the means between it's a sort of baseline slope, and then we add a bit for every different retailer. Because of that, we can see the differences in the slopes. And then down here, this is very similar to the model I had before for linear regression, with a couple of tweaks. One is that we're taking logs, because we're interested in the sort of difference rather than the absolute value of the sales as you put the price up. And the other difference is that down here, so this is the basic formula for doing regression, that we're saying it's the price times the slope plus the baseline B plus some noise. But the difference is that we've got retailer.slope. So we've got a different slope for every retailer that we're going to learn. So if you go ahead and run inference, we get a latent variable added to every store, which indicates the sort of the difference from the sort of the mean slope. And you see most of these are negative, but some of them are actually positive. And then you can go ahead in Excel and plot it. Go ahead and plot the result. So this is showing how the differences in different cities. So I think up in Albany, I think this is Albany here, and they're rather insensitive, that there's not much of a decrease as you put the price up. But in some other cities, this orange band, like down in New York, it's actually higher than the national average. So you see, within Excel, you can easily sort of visualize these kinds of differences. Yeah.
What other kinds of regressions have you all tried? Like Poisson, or have you just done a linear, or are there other examples that you all have?
we've been doing a great many. So we've been looking at stealing ideas from R. So R has these packages for linear regression that can, you can do hierarchical linear models and generalized hierarchical linear models. And we've been looking at stealing their notation to put them into tabular. I don't have any slides about that at the moment. But that's one, so when I said earlier that we were conscious that there was a bit of a gap here between what a machine learning PhD could do and what the data enthusiasts can do, I'm very conscious of that, and it seems R has done a nice job of nice notations for quite sophisticated regressions, and so we've been stealing those to put them in. But we don't have that ready for a talk right now. In general, here I'm talking about a fairly limited set of distributions, but we have a wide range of things like Poisson distributions and whole range for doing probabilistic modeling. Okay, so the next example that I'd like to do is another sort of variation on the true scale model, but looking at a kind of a very interesting model that looks at it's a kind of intelligence test where we've got a population of users. In this case, it was 120 participants, and there were 60 questions posed to them, and multiple choice questions. And we want to sort of learn the sort of ability of the participants with respect to these sets of questions, so it's a test. But we also want to learn what are the hard questions and what are the easy questions. And moreover, we even want to learn what the correct answers are. Perhaps not all the answers have been labeled. And so this model is rather interesting in that it can do all that at once. You can think of it, it's a bit like it's a model. It's a bit like the way some professors might operate. That you set a test for your class, and you're maybe a little bit tired and don't want to work out all the answers. So what you do is you know who your smart students are, so you go and look at their answers and then check them and then use that for the rest. I guess we're in a mixed company here between academics and industrialists. I'm afraid I'm a part-time academic, so I've sort of blown the professor's cover a little bit there. Please forgive me. So anyway, in this database we've got a table of responses, and for each response it's by a particular participant and to a particular question. Okay, so here is the difficulty ability model, where every participant has got an ability, which is done as a Gaussian, as before. Every question has got a correct answer, and which we can predict, and it also has a difficulty, which is another number. And then the model, you're maybe getting the idea by now, that we've got a model of responses, so we want to predict what the answer is, and we come in and we calculate the advantage. So this is the advantage of the participant over the question, and it's whether the ability is bigger than the difficulty of the question. And then and if that's greater than 0, we're going to assume that the responder actually knows the answer, otherwise they don't. So we have something called a probit function, which is a sort of noisy way of passing from a number to one. So it's sort of like a sinusoid. So if this is 0, the chances of the output being true is sort of 0, and then it kind of bumps up to being, and at 0 it's sort of 50-50, and then once you get a bit above 1, it becomes 1. Okay, so it's a sort of noisy way of turning a number into a Boolean. And then we have a guess. And then the basic model is, if the respondent knows the answer, then we give the correct answer. Otherwise, we just guess the answer. So this is a nice model, and it performs well. This is it represented in plate notation. And one reason I'm putting this up is to give it a comparison. So I want to evaluate this language versus writing it directly in conventional probabilistic programming languages. So this code out here is what you would write if you directly used our underlying system in Fur.net. So it's about 100 lines. Written in tabular, it's much shorter. And I'm going to put some nums up in a moment. Well, I'll put them up now, but we don't need to parse them in detail. The main point is that we get the same statistical answers with the same performance, but in much less code. So this is basically evidence that you might as well use tabular rather than directly using C#. Okay, so I started by saying I'm a language enthusiast, so I should put up a grammar. This is the grammar of tabular, and like I said, it's we're basically annotating the schema of the data. You can't do machine learning without data. You have a schema of the data. We're going to mark it up with the probabilistic model. So the schema is just a collection of table names with table descriptors. Big T is the table descriptor. Table descriptor is a list of columns. They've got types, and that would be it if it was an ordinary database, of course. But now we also have annotations, and I've gone through these different annotations in the talk, that you can have inputs and outputs, which are the observed data, and you need the inputs to be present, and we're going to predict the outputs from the probabilistic model M. We can have latent variables like skills. We can have parameters like the slope and the intercept of a linear model, and we can have hyperparameters, which are just constants that are used to configure the parameters or other things. If this has whetted your appetite for tabular, please download it and play with it and read our papers. And there you'll see how we we explain the sort of the full language, which has got function definitions and various kinds of conditional models, but I won't try and go into detail about them. And I think, let me see, I skipped a slide I wanted to show you, just to give you a feel. Oh, where is it? Oh, I know what happened. Yeah, this is, if you download it, it's a zip file. So if you have Windows and Excel, you can go ahead and run it. If you don't have Windows, download it anyway. You can open up the files, and there's a whole range that we've got. A bunch of different classification problems we can do. This is Bayesian linear regression. We've got logistic regression, if you know about these things. We've got naive Bayes. There's a whole bunch of different classifiers that have been written in this language. We've got various clustering algorithms. We've got principal component analysis, which is a way of taking a database with, a table with a great many columns and scrunching it down to a more significant representative sort of narrower table. And we've got various ranking models like TrueSkill, and lots of regression models as well. So it's at that URL. Please download and enjoy. Let me finish with this slide, which really just summarizes where we're going. That we want to empower users to learn from their data. Our models are just annotations on the relational schemas for data. And finally, we think that Excel or spreadsheets in general are a good place for manipulating data anyway, and so surely that should be the place where we should be doing machine learning. And I think, and I've shown you how tabular is a syntax designed to fit into the shape of spreadsheets, and let you saw what I was doing. You could just simply use the editing facilities to mark up your model and to run inference in place without having to go out of that environment to programming C# and whatever. So that's tabular. Do consider downloading it, enjoy it, and I'm very happy to take questions. Thank you.
So for your hypothetical data enthusiasts,
sure.
Do you think that they have the statistical sophistication to understand? I mean, assuming that the sort of user experience is improved and everything like that, like what is the sort of baseline knowledge they would need to be able to use this and not mislead themselves?
Sure, that's a good question. I think to use tabular seriously, you would need to have some understanding of probability distributions. So, you look out there. I mean, there's a tool called @risk for Excel, which is a sort of Monte Carlo inference system that assumes the user knows about normal distribution, well, Gaussian distributions, normal distributions, and so forth. So I guess we're going at people, of that sort of sophistication who, know a bit about statistics. Yeah. Oh, sorry. Go ahead.
Thanks. It seems to me that tabular isn't quite as integrated in the model of Excel as one might want. So typically in a spreadsheet, it has this sort of recomputation model where you change a value or you change a formula one place, and then those changes sort of percolate out through the rest of the spreadsheet sort of until it hits a fixed point.
Right.
Whereas here, you've really got sort of a batch processing paradigm where you highlight a region of cells and then say, tabular, do your thing, and then the output appears over here. And then if I go change it, I have to say, tabular, do your thing, and then I get my output again.
Yeah, that's true.
Is that something that you'd like to change in the long run? I mean, is the idea to sort of build Excel out to have recomputation for these models as well?
I would love to do that. We haven't attempted that in this version. We've had some earlier versions where we attempted to do that, and we used user-defined functions to build models within the cells. So, yeah, I mean, that would be a terrific way to go. So, yes.
So is a tabular program a representation for factor graph?
Yes.
And I understand that Markov logic networks are shorthand for representing factor graphs or something like that. Can you?
That's true, yes.
What's the difference?
What's the difference?
Yeah.
That's a good question. So a Markov logic network is like a particular kind of logic program. I'm not sure right now. I can give you an. I'll try and consider that and tell you offline. Yeah. Okay. If there's no more questions, thanks for your attention.